Good afternoon, everybody. Welcome you all to this post-noon session of International Conference on Recent Advances in Chemical Sciences. I am very happy to stand before you to introduce one of the leading scientists in the field of catalysis division. He is none other than our beloved Professor C. Gunanathan. He did his UG degree in BSc RKM Vivekananda College, University of Madras in the year 1997. He completed his master's degree in organic chemistry in University of Madras in the year 1999. In the year 2005, he completed his PhD in the Central Salt and Marine Chemicals Research Institute, India. About his achievements and awards. In the year 2011, he got Ramanujan Fellowship, served New Delhi. In the year 2016, he got ECRP award. He won first prize, 10,000 euro cash prize. In the year 2019, he got top peer reviewer award by Publons. The same year, he appeared among worldwide top 1% in the list of top 2% scientists. Give him a big round of applause. In the year 2020, he secured CRSI bronze medal. In the year 2020, he got Theme Chemistry Journals Award. In the year 2020, he was one of the top 3% highly cited authors from India in ACS. Give him another big round of applause. About his professional experience, in the year 2005, he was postdoctoral fellow, Weizmann Institute of Science, Israel. In the year 2006, he acted as Dean of Faculty postdoctoral fellow. He was Dean of Faculty Postdoctoral Fellow, Weizmann Institute of Science, Israel. In the year 2009, he was AVH Research Fellow, RUWTH Aachen University, Germany. At present, he is working with Nasir Bhubaneswar. He published 3 patents. And also he published 93 research articles in peer-reviewed journals. His H index value is 36 and his citations are 9,100. Now this floor is on your hands, sir.
this institution, namely Deaprtment. Particularly nowadays we are extensively working on base metal catalysis. For example, with cobalt, manganese, iron, and even simple base catalysis. But today I will be mostly talking about catalysis by ruthenium tensor complexes. So before going to the talk, let me thank all my co-workers. I have a couple of PhD students, and these are our master students. Our master students have the privilege of doing research for 2 years in 4th year and 5th year, and they publish fantastic papers, and they are all in very top universities in the world. And this year, 3 students went to the top universities in India for their PhD. And I have collaboration from Professor Walter Leitner and Dr. Alex Borden from Germany, and Dr. Xavier from West Canada, and Dr. Rosida Neil from IIT Palakkad. I also thank them for this opportunity. I also thank SRB India and Department of Atomic Energy as well as our NICER for generous funding in our research. So with this, I go into the work. I'm sure, may know, is there anyone here who don't understand Tamil? Sorry, who don't understand Tamil? Yeah. So can I speak in Tamil? Okay. So, இரும்பு தூணை பற்றி நிறைய பேர் கேள்விப்பட்டிருப்பீங்க, சில பேர் பார்த்தும் இருப்பீங்க. துருப்பிடிக்காத இரும்பு தூண் டெல்லியில் இருக்கு. This stands there as a symbol of cultural and scientific advancements that were there in our ancient India. And now I will show another iron pillar. I do not know how many of you know this. இந்த ஐரன் பில்லரை பற்றி தெரியும். இந்த ஐரன் பில்லர் மட்டும் இல்லைன்னா பூமியில மனித இனம் வாழ்ந்துகிட்டு இருக்கிறதே கேள்விக்குறியாயிருக்கும். ஏன் சாப்பாடு இல்லைன்னா நம்மளால கொண்டாடவே முடியாது. ஒரு 100 வருஷத்துக்கு முன்னாடி food production became a really question whether population growth was keep on increasing, whereas food production was minimal. So the price rise was phenomenal, like it's happening now because of distribution and Ukraine war. So அது எப்படி சால்வ் பண்ணாங்க அப்படின்னா தான் சால்வ் பண்ணாங்க. ஆக்சுவலாக இது ஒரு இரும்பு தூண் கிடையாது, இது வந்து அமோனியா ப்ராசஸ் ப்ரெஷர் ரியாக்டர், ஐரன் ரியாக்டர். இந்த ரியாக்டர் தான் வந்து அமோனியாவை வந்து லார்ஜ் ஹெல்ப் பண்ணுச்சு. இந்த Taper ammonia process, it is the only process that got 3 Nobel Prizes. There is no other reaction has that much privilege, because the scientific community recognized that this is the process that saved the entire world. Okay, so this reactor allowed to produce enormous ammonia that allowed the scientific community to produce enormous fertilizer, and from that the food production was enhanced to meet the requirement of this population growth. So that allowed this phenomenal population rise on the entire third world sustainable. It was only because of this reaction. So similarly, the petroleum refinery employ large amount of catalytic processes. But the petroleum industry also employ different catalytic processes that provide various life-saving chemicals that we are using for starting from space. Instead of large-scale catalytic processes, they are not producing any waste. They are actually green technologies. On contrary, the pharmaceutical industry, which employ the linear organic synthesis, they produce huge waste, environmental waste. This is a really problem to the environment. So there is an imperative need that we develop new catalytic reactions that do not produce any waste, so that the conventional organic synthesis that create waste can be replaced by this kind of green catalytic reaction. So with this, we are constantly developing simple organic reactions with catalyst and without generation of such waste. In most of the reactions, the only byproducts are water and or molecular hydrogen. So we don't produce any other waste. In some of our reactions, there is no byproduct. Economic product. With this, I introduce some of the fundamental concepts that required to understand our research. Metal ligand cooperation. What is metal ligand cooperation? In general, in organometallic catalysis, the ligand do not participate in the reaction. metal catalyst in which not only ligand, not only metal, also ligand participate in bond activation and bond formation process. Such processes are called metal ligand cooperation, and such metal ligand cooperation has its origin in enzyme catalysis. For example, I have shown one example where the electron reduction of two protons leading to molecular hydrogen has a cooperation from the amine ligand. As you see, this is a simple amine, and that allows the proton to become like it acts as a proton acceptor. Further, that proton is transferred to the metal center, leading to the reduction of the one electron reduction to the metal, leading to the creation of molecular hydrogen. So this is one of the examples where the amine arm in the enzyme act as both proton acceptor and donor, resulting cooperating hand to the metal. So both metal and ligand cooperate together to create the catalytic process. Next. So the chemist love to mimic nature. So accordingly, Xavier is pioneer in metal ligand cooperation. He is also a Nobel Prize in polarity in catalysis, and developed this catalytic process in which this lithium amide complex reacts with molecular hydrogen that forms a non-classical hydrogen coordinated lithium complex that splits the molecular hydrogen across the metal and amide arm, leading to the formation of lithium dihydrate and amine ligated metal complex. And this complex transfers both hydrate and proton concomitantly to the polar organic functionality, leading to the reduction of the carbonate molecule to corresponding aldehyde. Similarly, in this, the amide ligand becomes amine, and both metal and ligand helps each other to carry out the catalytic transformation. So this is metal ligand cooperation. So there are also other similar catalysts reported in the literature, which all employ via this different kind of metal ligand cooperation. There are so many catalysts nowadays. I just give the binary examples reported in the literature for metal ligand cooperation. And then why pincer complex? There are simple metal precursors which can also act as a catalyst, but achieving selectivity with such metal precursors are very challenging. There are simple designed catalysts with monodentate ligand and bidentate ligands. They are also very good catalysts, but they also have the limitations at high temperature. At elevated temperatures, such complexes will undergo decomposition, losing its integrity as well as reactivity. Whereas the pincer complex that has a bidentate coordination, it is bound tightly that this when the bidentate ligand that coordinates to the metal center enforce a meridianal geometry on the metal center that enhance the both stability of the complex as well as the reactivity. So the also exhibit metal ligand complex. For example, this ESP lithium complex amount of base, we have developed Oates mode activation of water as well as Oates mode activation of alcohol. And based on this Oates mode activation, we have developed the catalytic process for the selective incorporation of deuterium into organic molecules, in which we have used deuterium oxide, heavy water, as a deuterium source. Heavy water is the cheapest deuterium source. However, deuterium incorporating deuterium into organic compounds directly from deuterium oxide is very challenging, because most of the organic compounds do not even mix with water. So deuterium oxide has to be converted to other deuterium compounds like methanol D or chloroform D, and from that deuterium has to be incorporated into the organic compound. This is it's easy to say, but practically this is a very challenging process, and as a result, the resulting deuterated chemicals are very, very expensive. For example, benzyl alcohol, 1 bottle you can get, like 1 liter bottle you can get for 50,000 rupees. But if you want to purchase 1 gram of benzyl alcohol deuterated, it will be 25,000 or 50,000. So this multi-step synthesis involved in incorporation of deuterium, it enhances the deuterated price enormously. So if you can introduce deuterium directly from deuterium oxide, this will be very, very beneficial. That's why we have done directly from deuterium oxide. We would incorporate deuterium into alpha position of primary alcohol, as well as alpha and beta position of secondary alcohol selectively. Again, the selectivity is the key here. And similarly, we would selectively incorporate deuterium into terminal alkane functionality for the first time in a catalytic manner. And in that, we have also established the ruthenium acetylate intermediate. We could isolate this intermediate and characterize it with H-like crystal structure, this ruthenium acetylate. And in the integration of nitric, we could also insert such involvement of such 2+2 cycloadactyl integration of simple alkyl nitrile compound. Once again, in a linear chain aliphatic nitrile compound, we could selectively incorporate deuterium only at the alpha position. So, further, using this ruthenium macro catalyst, we could selectively get formyl CH activation, where the reaction of the base undergoes Wilkinson halogenation reaction, and this unsaturated intermediate reacts with dimethyl formamide and presumably forms such formamide complex, which is unstable, and we always end up having this such ruthenium dichloride metal complex. So we could detect the carbon monoxide formed in situ the reaction from the dimethyl formamide. We know carbon monoxide is very toxic, and using it directly in the reaction is difficult. Further, using the same complex, we have also achieved the selective NH bond activation. This NH bond activation is very challenging, whereas here at room temperature, in a very facile manner, the amine reacted with this unsaturated metal complex and formed this amide complex at room temperature. Very facile reaction. So as you can see that out of the 2 protons that amine has, 1 proton is cut off, and that now is bonded to the backbone amide nitrogen to become amine. So we have formyl CH activation and NH activation. We integrated to create a new catalytic process for the synthesis of urea derivatives. As you can see, we have used dimethyl formamide as a surrogate for carbon monoxide, which is toxic. So we don't need to use carbon monoxide, we can simply use dimethyl formamide in the reaction, and through the formyl CH activation and NH activation, we could develop a catalytic process for the synthesis of urea derivatives, in which the only byproduct is molecular hydrogen. Very interestingly, we can intervene the reaction, and after monoformylation, we could incorporate a different amine, primary amine, that will produce synthetically challenging unsymmetrical urea derivatives. This is very difficult to get unsymmetrical urea derivatives by a conventional synthesis. Whereas through this catalytic method, we can get very good unsymmetrical urea derivatives in good yield. This is the proposed mechanism where the involvement of this unsaturated intermediate is established by mass spectral analysis. Further, the NH activation, I have already shown that we have even characterized the intermediate by X-ray crystallography and NMR analysis. And this amide complex further reacts with carbon monoxide that comes from activation of CH bond in formamide, dimethyl formamide, and the formation of carbon monoxide was independently checked even in catalysis via GC analysis. So, in situ formed carbon monoxide from dimethyl formamide undergoes this bond insertion into ruthenium amide bond to generate this ruthenium formamide complex. So, this formamide complex, this amine does conjugative nickel intermolecular nucleophilic substitution. So, that nucleophilic substitution generates the urea derivative, leading to the generation of this ruthenium dihydrate intermediate. And this ruthenium dihydrate intermediate can liberate a molecular hydrogen to become this unsaturated complex. So, this independently, the formamide also established by performing the reaction at low temperature. If you do the reaction at 135 degrees Celsius, we tells that the reaction indeed goes via this monoformamide intermediate. In general, the removal of protons from adjacent centers of organic molecule is a thermodynamically challenging process which requires stoichiometric amount of oxidants, metal salts, additives, and all this reagent in large excessive amount, leading to the generation of copious inorganic waste. So, in order to avoid this waste generation, people have come up with the catalytic method, which also used sacrificial acceptor molecules that also led to the generation of sacrificial amount of waste. In many cases, the only thing that sacrificed in the reactions are more valuable than the product that created by dehydrogenation reactions. These are such sacrificial acceptors are necessary to manage the thermodynamics involved in the reaction. Without this sacrificial acceptor, the reaction won't go with those catalysts. Whereas the advancement of organometallic chemistry over the years, state-of-the-art catalysts were introduced which have the ability to create molecular hydrogen in situ, as the molecular hydrogen is a gas that can be effectively removed from the reaction system. The removal of, there are two reactants. To remove one reactant from the reaction system, that will shift the equilibrium towards the product formation. So that is the concept listed here. So, and then based on this, the strategy is called acceptorless dehydrogenation strategy. So, based on this acceptorless dehydrogenation, several synthetic strategies were developed in organic industry. One such strategy is the borrowing hydrogen concept. In this concept, the catalyst oxidates alcohol to aldehate or secondary alcohol to carbonyl compound. And the instead generated carbonyl compound will undergo condensation with the different nucleophile to generate intermediate, and this instead formed intermediate will be hydrogenated by the hydrogen obtained from alcohol oxidation. So, hydrogen borrowed from alcohol oxidation. So, that's why it's called a borrowing hydrogen concept. So, that will hydrogenate to be the saturated product. So, using this concept, we could selectively alkylate the different nitrile compounds using primary alcohol as an alkylating agent. You all know that for simple alkylation reaction, you need alkyl halate or alkyl tosylate as an alkylating agent. It has to be derived from alcohol. Whereas here, we directly employed alcohol as an alkylating agent, and the only byproduct is water. So, there is no waste generation here. And the amount of waste is calculated about 1 mole percent, and the catalyst load is just 0.5 mole percent. As you can see, highly functionalized alcohol or mediating alcohol can be used, and the yields are really good here. Further, we could also perform challenging ethylation and methylation reactions. Like those who studied organic chemistry know that methylation is one of the very difficult reactions. You need to use methyl iodide. Its boiling point is less than 40 degrees Celsius. So, if you do reaction in critical ready, the moment you open methyl iodide bottle, it will open. So, it's really challenging. So, we could do such methylation reaction using methyl alcohol. Very simple. You just put methyl alcohol, reflex, you will get methylation. And such methylation reaction also have a possible pharmaceutical application in synthesis of such drug molecules. It is the propulsion mechanism. The initial form intermediate can react with nitrile in a 2+2 cycloaddition, leading to the formation of cycloattack. The The evidence for this I have already shown in the previous slide. So this cyclodeck can exist in equilibrium with its enamine form, and the same intermediate can react with alcohol and undergo OH bond activation. This alkoxy intermediate also we have already shown that we have achieved the OH bond activation from alcohol. And this alkoxy intermediate can undergo beta hydride elimination and to generate a aldehyde intermediate. This aldehyde will undergo conjugate addition with enamine, generating this enamine adduct, which will be hydrogenated by this ruthenium dihydride to generate a alpha alkylated compound directly from alcohol. Further, very interestingly, when we use the secondary alcohol in this reaction, the only difference is we have changed the alcohol from primary alcohol to secondary alcohol. This use of secondary alcohol results in enhanced steric hindrance at the beta position. When there is a tetra substitution on the alkene, this molecule does not fit into the catalyst bucket. As a result, the reaction is prevented at the olefin stage. So instead of borrowing hydrogen strategy, now we have acceptorless pre-hydrogenation strategy, and the reaction produces both water molecule reaction as well as liberation of molecular hydrogen. The hydrogen obtained from alcohol oxidation is not reused, it's liberated. So as a result, we have explicit vinyl nitrile formation directly from nitrile and alcohol. Very interesting. The reaction is also applicable to the aliphatic nitrile compound. This is a very challenging synthesis to obtain vinyl nitrile directly from aliphatic nitrile compound. And the reaction applicable to both cyclic alcohol and even acyclic symmetrical as well as unsymmetrical secondary alcohol. The kinetic analysis indicates that reaction proceeds via oxidation of alcohol. The in situ found cyclohexanol from hexanol is concomitantly used in the reaction. This is the cyclohexanol intermediate, whereas you see the very short formation of this product, whereas this molecule is the moment it forms, it gets utilized in the reaction to generate the condensation product. Similarly, we have reacted secondary alcohol with the hydrogen hydrate, where the generated ketone and hydrogen underwent condensation to produce the ketone products directly from secondary alcohol and hydrogen. And once again, the only byproducts are water and molecular hydrogen. As you can see, cyclic secondary alcohol or even acyclic secondary alcohol and even functional group containing secondary alcohol all beautifully react. Further, the cyclic aliphatic secondary alcohols also reacted very nicely. You can see that many ketone products with the cyclic alkane, and even the simple isopropanol can be used in the reaction. This is very challenging considering the low boiling point of isopropanol. And very interestingly, even the ketone can be obtained from cholesterol, in which very interestingly the double bond in the D ring in cholesterol is migrated to the A ring due to the extended conjugation in the ketone product, and we have the X-ray crystal structure of this product to establish its structure. Very recently, we could also couple alcohol with hydroxylamine. You know, hydroxylamine is a very unstable compound with very low nucleophilicity. Other the nucleophiles that we used so far, nitrile are very strong nucleophiles, whereas hydroxylamine is not a strong nucleophile. So because of this, we have to use up to 5 moles of catalyst, but still getting oxime product directly from alcohol and hydroxylamine is not easy synthesis. You know, oximes are very, very important because oximes are in general, earlier it was used for the in the Beckman rearrangement, which is very important for textile industry. The nylon 66 is actually produced via Beckman rearrangement. So we could selectively get oxime product directly from primary alcohol and hydroxylamine hydrochloride salt. You know, like you don't get pure hydroxylamine. Because of the instability, always comes as a hydroxylamine hydrochloride salt. So we have to use stoichiometric amount of base to neutralize hydroxylamine hydrochloride hydroxylamine, which will be further used in the reaction. also recently there are no, all our catalyst oxidation is true, and the beauty of our catalytic process is the oxidation remains true in all the steps. That is the beauty of this metal ligand complex. When amine becomes amide, the valence is neutralized. So oxidation state remains from none of the our catalytic steps involve oxidative addition or reductive elimination. It's all formal oxidative addition, formal reductive elimination. Where the metal oxidation state remains the same. In recent time, there are development of, for example, cobalt, manganese, iron, nickel. All those catalysts are being employed. This is ourselves. I will show at the end that we ourselves work on those. But still, in terms of efficiency, resilience remains very important. So, using the hydroxyl, we have made very good octanes with a good functional group. Very interestingly, using the catalytic method that we have developed, we could prepare this dopamine binding receptor in which we have employed our own catalytic method in a multi-step organic synthesis. So not only we developed the catalytic method, we have also used that method in application to synthesize organic matrix. From that, the acyl hydrates are extensively used in heterosynthetic chemistry, pharmaceutical chemistry, and even in material synthesis. Whereas there was no catalytic method known for synthesis of acyl hydroxides. The known methods of alcohol has to be converted to alkyl halide, then alkylation reaction has to be performed with the stoichiometrically excess amount of base. So we envisage using our catalytic method, we could directly incorporate N-dialkyl functionality on the acyl hydrogen. So employing the next slide please, we are doing something that prevents me. Yeah, no. As you can see that we have used two current of alcohol, just 2 moles instead of catalyst, and on the acyl hydrogen we could directly incorporate N-dialkyl functionality, and once again the only byproduct of 2 molecules of water. As you can see, linear alcohol, branched alcohol, and even having sensitive functionalities like alkene can be tolerated in the reaction, and even fatty alcohol can be applied. And very interestingly, the challenging challenging ethylation as well as methylation reactions can be performed using ethyl alcohol and methyl alcohol. We can do diethylation and as well as dimethylation reaction on the acyl hydrogen. Interestingly, next slide please. Interestingly, once again we can intervene the reaction after monoalkylation, and we can stop the reaction and introduce different primary alcohol, and we can have unsymmetrical N-N dialkylation reaction performed on acyl hydrogen. As you can see that both primary alcohol and secondary alcohol can be used. In that case, we have to use the secondary alcohol first, then we have to use the primary alcohol. The reverse is not working. Like once you introduce secondary alcohol, then primary alcohol can only be used. If you do primary alkylation first, the secondary alcohol cannot be incorporated because of the steric hindrance of the substance. Interestingly, when we use the sir, please move if you are blocking my actually you are doing something that prevents me, man. alcohols in this reaction, we directly obtained heterocycle containing acyl hydroxides, and such motifs are predominantly present in pharmaceutical compounds. The next is cross-coupling of alcohols. The cross-coupling of primary alcohol and secondary alcohols are well known in the literature. The self-coupling of primary alcohols also well known in the literature. It's called Cuthbert reaction. Whereas cross-coupling of two different secondary alcohols remained unknown in the literature. We solved this problem employing this our ruthenium macro catalyst, where we reacted two different secondary alcohols to get synthetically valuable beta dialkyl substituted ketones with liberation of molecular hydrogen and water. As you can see, by reacting acyclic secondary alcohol with a cyclic secondary alcohol like cyclohexanol with different ketones, different aryl ethanol, we could couple the product to get the cyclohexane alkylated product with very good yield. Further, in such reactions, we have also observed product-induced diastereomer selectivity in the reaction. For example, as you can see in the crystal structure, the newly formed carbon-carbon bond is cis to the existing methyl substitution in this product. So accordingly, similar stereochemistry is assigned in the other products, and very interestingly, even the hetero-aryl secondary alcohols and simple acyclic aliphatic secondary alcohols can be cross-coupled to form the beta disubstituted ketone product in very good yield. And this is the first catalytic cross-coupling of two different secondary alcohols. In the mechanics study, when we employ this highly hindered adamantanol, the reaction stops with the quinone formation. Further hydrogenation was not possible. When we reduce this very hindered adamantanol to peptanol, indicate indeed the reaction proceeds via this alpha beta unsaturated ketone intermediate. Further, when we use the deuterium labeling on both secondary alcohols, the kinetic analysis indicates that the oxidation of this aliphatic secondary alcohol undergo much faster than this aryl ethanol. Mechanism in which the coordinatively unsaturated intermediate reacts with generates alkoxy intermediate, which does undergo beta hydrate elimination, generating this ruthenium dihydrate, two equivalent from both alcohols, and the in situ formed ketones undergo aldol condensation to form this eno, which hydrogenated by this ruthenium dihydrate to generate this beta disubstituted carbonyl compound. Alkylation of ketones by primary alcohol very well established in the literature, but ketone alkylation using secondary alcohol, there were only 4 reports in the literature using iron, cobalt, manganese catalyst, and the first one was with iridium. This is the question that you asked. All the 4 reports required superstoichiometric amount of reaction. Not only that, on the ketone there must be minimum 2 substitution at the both ortho and ortho prime positions. Without this steric hindrance, the reaction will not work. And in fact, all the reported 4 papers use the penta substituted phenyl rings. This is very important to avoid self-coupling of ketones, because the reaction requires aldol condensation, and the ketone itself will undergo aldol condensation. To avoid this self-coupling, they need high level of steric hindrance on the substrate. So, like all these are competing side products coming from aldol condensation, and the desired product itself coming from aldol condensation. So, controlling the selectivity in the reaction is very, very crucial. Whereas, the experience that we gained from cross-coupling of 2 different secondary alcohols, different secondary alcohol alkylation to carbonyl compound, as you can see that for the first time we could alkylate the simple ketone as acetophenone. As you can see, there is no substitution on the phenyl ring now. Earlier, there was not a single report where the non-hindered ketones are employed in such reactions. Whereas first time, Xavier who came from SXC to develop a method where the ketones can be selectively alkylated using secondary alcohol, and the only byproduct is again water. So not only simple acetophenone, also other aryl ketones, even functionalized the phenolic ketone or naphthyl ketone, other sensitive functional groups containing even pyridine containing ketone, all can be employed. And the reaction is not only limited to unsubstituted ketones, even the peripheral ketones which employed in other reports can also be employed in this reaction very nicely. Very recently, Xavier also selectively incorporate pyrenylation on the ketone using pyrenol. Actually, this is a very challenging transformation. You may think that both are alcohol, but actually we have allyl alcohol. Upon oxidation, you get acryl aldehyde, and acryl aldehyde is a super reactive substrate that will generate 9 different possible side products. So, getting such selective alpha pyrenylation directly from pyrenol, there was no report, and this is the first such report developed by Xavier. As you can see, highly functionalized ketones, even heteroaryl ketones can be selectively pyrenylated using pyrenol as a direct pyrenylation reagent. And this work was very much appreciated, and the journal OPC also invited us to submit a cover page, and that was accepted and published as a cover page in Organic and Biomolecular Chemistry, and this image is itself created by Xavier. Another method where we could selectively alpha alkylate beta naphthol using alcohol as alkylating reagent. Once again, this is a very challenging process because alkylation of arene is not an easy process, and that too coming directly from alcohol as alkylating reagent. And as you can see, even functionalized alcohol, like such carbazole methanol can be used, directly alkylated on the beta naphthol, and even such functionalized heteroaryl compound, even such metal containing alcohol can be directly alkylated, and even the aliphatic alcohols can be directly alkylated on the beta naphthol, which only being water as the byproduct. The reaction mechanism is very complex, and this mechanism is extensively studied with the help of Dr. Roshida in IIT Palakkad using DFT calculations. And the calculation suggested that the stoichiometric amount of base as well as the in situ formed water helps the reaction, because the proton transfer from the catalyst to substrate, this is a very crucial step, and the in situ formed water itself facilitated the further reaction. As you can see that the unsaturated intermediate reacts with alcohol to generate this dihydride, and which generates this aldehyde, and the reaction optimization is very key to success of this process. Upon using different phases, only lithium third butoxide was efficient in this, because the lithium beta naphthalate that generates has the ability to create a small amount of this corresponding keto compound. Here there will be a carbonyl, and methylene carbon will be generated at this alpha position. That carbonyl methylene compound undergo aldol condensation with aldehyde to generate such intermediate with liberation of water, and such stabilization was possible only with the lithium butoxide. No other place of efficient in this. So once we have this compound, this intermediate was we could observe the involvement of this reactive species by NMR. Like if we do low temperature NMR, we could observe the species involved in the reaction. Further, the ruthenium hydrate is transferred to this beta position that generates this kind of naphthyl oxide, to which the amine proton is transferred to create the such alpha alkane beta naphthyl product. So in all the reactions that we have talked about so far, we have either water or molecular hydrogen as the byproduct. We have also asked the next question that can we avoid even the formation of water and alcohol and preserve economy and resource. So this question allowed us to establish a new strategy. We have employed allyl alcohol instead of simple alcohol, primary or secondary. So once we use this allyl alcohol, upon oxidation, this generated alpha beta unsaturated ketone instead of aldehyde or ketone. So this alpha beta unsaturated ketone underwent 1,4 conjugate addition instead of condensation that was observed in previous reactions. So this conjugate addition generated a delta oxonitrile, and this nitrile, this oxo functionality is hydrogenated with the hydrogen molecule obtained from allyl alcohol oxidation, and we got delta hydroxynitrile compound with 100% atomic economics. So as you can see, alcohol reacted with highly functionalized different nitrile compounds, and we got delta hydroxy nitrile compound with excellent yield, and this work was established by both Deaprtment, and Deaprtment is the student who brought the base under to my group, and both of them together developed this fantastic work, which was very much appreciated by the scientific community. Not only primary allyl alcohol, even the functionalized primary allylic alcohol and secondary allylic alcohol can be used in the reaction. As you can see, even aliphatic allylic alcohol or functionalized allylic alcohol can also be employed in the reaction, even having a sensitive functionality like fluoro or vinyl functionality. And interestingly, we can also perform double conjugate addition reaction leading to the construction of quaternary carbon center when there is electron withdrawing group or thiophenyl nitric compound. So using this formal conjugate addition catalytic method that developed in our group, we could look at various synthetic receptors that are commercially available, and even the commercially available drug molecules. This drug synthesis are observed attained in very short synthetic method using this catalytic method developed in our group. Very interestingly, you can see this anivamine drug where both alkylation as well as conjugate addition both are attained by using the same catalyst. Earlier we have developed alkylation of beta naphthalene using this catalyst. Then we developed conjugate addition. Both methods are employed in this catalytic synthesis of this drug molecule. So we are very fortunate to have such molecules, and even other drug molecules also we could synthesize using this catalytic method. Once again, this is the reaction mechanism is very complex, established with the help of Dr. C.H. Suresh by EFT calculations. The institute formed intermediate reacts with allyl alcohol via agnostic interaction leading to the OH bond activation as well as concomitant CH bond activation, generating this acryl aldehyde intermediate which undergo condensation with base promoter condensation reaction to generate this delta oxo nitrile compound, and this aldehyde functionality again coordinates with the ruthenium dihydrate complex leading to the series of reactions resulting in reduction of carbonyl functionality to alcohol functionality. We could selectively reduce epoxide to secondary alcohol. Once again, the catalyst have the ability to discriminate the epoxide in such a way that the reactions are applicable only to the terminal epoxide. Internal epoxides do not work. Very interestingly, even the aliphatic epoxide, terminal epoxide, and diepoxides can be selectively reduced to diol products. Interestingly, the catalyst has the ability to discriminate the terminal epoxide in such a way. The reaction works under high pressure hydrogen gas condition. The hydrogen generates this ruthenium dihydrate intermediate, which reacts with epoxide in such a way the amine proton is transferred to the epoxide oxygen, and the hydrate is transferred in such a way the hydrate approaches only the left hindered terminal carbon leading to the internal alcohol. This is the key step. If the hydrate is transferred to the internal carbon, then we will have a even more valuable linear alcohol. The linear alcohol has much more importance in industry than secondary alcohol, but we were not that lucky. We got only selectively secondary alcohol. So with this, I conclude my talk on ruthenium catalysis. Using the simple ruthenium macro catalyst and catalytic amount of base, we could selectively incorporate lithium into different organic compounds via OH bond activation of water as well as alcohol. Further, via forming CH activation of DMF and amine, we could develop a catalytic process for the synthesis of urea derivative, and also achieve the sp synthesis as well as permanent dialkylation of acyl hydrogen. Also, recently we have developed oxygen synthesis directly from hydroxyl hydrochloride and selectively reduce secondary secondary epoxide to secondary alcohol. And then, using the same catalyst, we will selectively perform monoalkylation of nitrile and then nitrile synthesis directly from nitrile compound and secondary alcohol. And we have also discovered the cross-coupling of two different secondary alcohol to beta disubstituted ketones. And similarly, we could selectively alkylate the ketones using secondary alcohol to attain similar beta disubstituted ketone compound. And recently, the pyranylation was attained using prenol as a direct pyranylation reagent. And we have also observed delta hydroxynatyl synthesis directly from allyl alcohol and nitrile compound. And recently, we have attained the selective alpha alkylation of beta naphthol, in which we have used primary alcohol as alkylating reagent. And further, we are also developing another catalytic method involving beta naphthol, which will disclose maybe if you invite me as next time. Further, we are also extensively working on hydroelimination reactions. In this reaction, we have uncovered the involvement of this ruthenium hydrogen-rich dinuclear intermediate for the first time. There were hydroeliminations reported several times in the literature, including this ruthenium paracetamine precursor, but no one observed involvement of such intermediate. And we have observed this intermediate for the first time in 2014. Then we established a series of hydroelimination reactions, and in all these reactions, this is the two intermediate involved in involved. Interestingly, we could develop a catalytic method for the borosiloxane synthesis directly from borane, silane, and water as the oxygen source, and the only byproducts are water and molecular hydrogen. And the involvement of water, we labeled the water with oxygen 18, and we confirmed that the oxygen indeed comes from water. And even more excitingly, we could establish the addition of boron hydrogen bond across the sp3 carbon oxygen bond for the first time in the literature. This developed a new reaction called hydroboronolysis, where we could cleave the saturated ether to alkane and boronate ester. We also employed this hydroelimination reaction for the selective de-aromatization of heteroaromatic compounds. As you can see, the pyridine compounds are selectively 1,4 de-aromatized via 1,4 addition of hydrogen and mineral borane. And such, I just represented the examples. Any pyridine having 2 and 3 substitutions are tolerated in the reaction, and the reaction works beautifully with such simple pop sandwich with the catalyst. And very recently, using the same catalyst, when we did hydrosilylation reactions, very interestingly, the reaction worked via 1,2 hydrosilylation reaction. This has much mechanistic significance. Even 1 hour is not enough to discuss all the process involved in this. And once again, this mechanism is established with the help of Dr. C.H. Suresh, who uncovered the involvement of tetral bonding mechanism in such hydroelimination reactions for the first time in the literature. This is very interesting work that we could solve that problem with the help of Suresh. As you can see, not only pyridine, any heteroaromatic compound. I just gave only two examples lack of time. Like any nitrogen containing heteroaromatic compound can be selectively 1,2 hydrogenated using this different silane. Silane can also be employed in the reaction. We are also working extensively on base metal catalysis in recent times, where we using manganese tensor catalyst, we could selectively perform both cross-coupling of primary and secondary alcohols, leading to alpha alkylation reaction, and also selectively incorporate vinyl functionality like alkylation using alcohol as a alkylation reagent. You know, like olefin synthesis is a very challenging problem in organic synthesis. There are only few methods available for olefin synthesis. You need Wittig reaction. You know, like Wittig reagent is it involves phosphorus, and you need large excess amount. Whereas no Wittig reagent, no functionalization, just you use primary alcohol, and you can perform range of alkylation reactions, and the only byproducts are water and molecular hydrogen. Further, we are also extensively working on cobalt pincer catalyst. This is our own catalyst, a simple catalyst, and with this catalyst, we could selectively perform the cross-coupling of silane as well as silanol leading to siloxane synthesis as well as monohydroxysiloxane. Only byproduct is molecular hydrogen. For that, we will selectively oxidize primary alcohol to carboxylic acid, and once again, the only byproduct is molecular oxygen. And we could selectively hydrogenate ester into aldehyde functionality as well as primary alcohol functionality. This 100% selectivity can be achieved, in which the stoichiometry of silane helps us to achieve the selectivity. This is a very important reaction because to catalytically synthesize aldehyde, it's a very challenging problem, and there are only few methods available in the literature. And very recently, once again, this is a first of its kind reaction where the ethers are converted to secondary alcohol. This is a 1,2-Wittig reaction in conventional method. In 1,2-Wittig reaction, we need a stoichiometric amount of lithium metal. Whereas using catalyst, this is the first catalytic method for Wittig reaction, which created secondary alcohol directly from ether. So with this, I just wanted to show our campus, which is nicer Bhubaneswar. This is the front view of our campus. This is as you can see, this is the entrance. We have only one entrance, so 300 acre campus. And the space that you see is 2 kilometers away from us actually. This is called Andheri Delhi. And the small boxes that you see, that is IIT Bhubaneswar. We are 2.5 kilometers away from IIT Bhubaneswar. As you enter this campus via this entrance, we have the our entire campus. We have a small hill inside, and we have a meditation center on top of the hill. And the campus is built around this hill. As you can see that the first building is a director office or admin building, and then across this is the chemistry building, this entire building, and this is the biological science and School of Chemistry. And in the middle, we have a state-of-the-art library. Like that looks like a five-star hotel. Beautiful and amazing library that we have. And after that, this is the library that we have. After that, School of Physical Sciences, School of Mathematical Sciences, and we have a state-of-the-art auditorium that can accommodate so many people. And it's one of the best auditorium available in Odisha. So this is our Indian campus. You see Vijay and Arunachalam, who did PhD in CS Engineering and spent a very short time with us. Now he is in Reliance Industry as a scientist. So we have two people from Tirunelveli, Arunachalam and Vijay from Tirunelveli, and Vijay is from St. Xavier PSC here. And this is my Indian group. And many are Manas Kumar, Subham joined PhD in US. Hariharan came from Barbika University and Arunachalam, and he is Arijit, who is a master student. Priyanka is also my current final year master student. Deepak Kumar Sabu, who came from IIT Bombay, doing PhD with me. Sandeep already completed PhD and working as a scientist in Nucleides Pharma. And Anurag Kumar joined USCAP just in the US, and Pushpa and Manik will continue working for PhD, and he is applying for PhD program. So to this, I really thank you. I'll be happy to take questions.
Sir, you have conducted all the reactions in neutral medium, isn't it? You have conducted your reaction neutral medium, isn't it? Medium, neutral medium. Is there any reason behind it? Of course. Thank you, sir. Thank you, sir. Is there any other question?
first of all, congratulations, sir. It was a great presentation. So I had a small doubt. So most of the cases in first part of your work, you have used potassium tertiary hydroxide, sir. So is there any specific reason behind that?
So at one point you used an alkene which is called as sacrificial acceptor, and another side it is sacrificial base. So what is the reason for putting both sides as sacrificial?
Alkene is without alkene no reaction. Alkenes are essential to manage the thermodynamics involved in the reaction. So once you alkylate, then it's a the corresponding alkane. It's just only. Okay. The real problem is many times this alkene that are used are more expensive than the de-adenosine product that you obtain from another alkene. Yeah. That's why it's waste. Yeah. You not only create a functional group, you also kill the value of the valuable compound. No questions. Once again, I thank the our senior colleagues for the kind invitation and great hospitality. I also give my best wishes to the young students. Study chemistry with a lot of inspiration and interest. You'll have a beautiful future as well as career. Good luck.
Dear sir, we are really impressed by your lucid presentation. Hope our audience would have been benefited out of this lecture a lot. It is really an eye-opening session in the field of sustainable catalytic transformation, especially on ruthenium complexes. The very interesting thing is, in one of your research synthetic procedure, you have achieved 100% atom economy. Thank you, sir. Now the session is technical session 6. Now I invite Dr. James Ruben to introduce the speaker.
Good evening. So this is the final session of the day. Dr. T.S.T. Balamurugan is waiting for us from Poland. So I'm very happy to introduce him for the audience. So here we have Dr. T.S.T. Balamurugan. He is our illustrious alumnus. He received his BSc Chemistry from this campus from Xavier's College, Palayamkottai. After completing his BSc Chemistry, he moved to Bharatbhasan University to pursue his master's degree. After completing his master's from there, he moved to Taiwan for his PhD, and there he did his PhD in the topic analytical and electrochemistry from the National Taipei University, Taiwan. After completing his PhD, he has spent a brief period of postdoctoral fellow in the National Taiwan University and National Taiwan University of Science Science and Technology. And he worked and designed in custom-made lithium-ion batteries and triboelectric nano generators for green energy applications. Currently, he is a Mary Stoddard Curie Action Era Fellow, come research assistant professor at the Faculty of Chemistry, University of Lodz, Poland. So during his past 6 years as a researcher, he has published more than 20 research articles with 600 plus citations with height index of 15. His field of research interest includes molecular designing, surface engineering, activity-based biosensing, and developing portable analytical devices and 3D printing. So such a wonderful personality is here with us. Now I request Dr. Balamurugan to talk in the topic, the emerging electroanalytical platform for sensing applications. So on behalf of the Department of Chemistry and the management and the participant present here, I welcome Dr. Balamurugan for the presentation.
Thanks for the introduction, Professor, and good evening, everyone. I'm here to give my talk today about electrochemistry of soft interfaces as an emerging analytical platform for data and drug screening. So my talk is going to be divided into 5 simple topics. I can understand it's a pretty long session. We have some very great lectures with high quality content over the last 5 hours. So I have to be light and quick as possible. So my talks have been 5 titles. It's I'm developing a sensor for screening date and rape drugs. So what is date and rape drugs? So they are a class of illegal drugs and it's also associated with drug-related sexual assaults. And title 2 is sensors. What is sensors and what is electrochemical sensors? And title 3 is electrochemistry at soft interface and how it works. And I demonstrate illegal drug sensor at electrochemistry using electrochemistry at soft interface and what's the future perspective of the work. So start with the illegal drugs. The data of the possession of illegal drugs around the globe is very common and it leads to numerous civilian problems and crime activities. You can see the various illegal drugs ranging from opiates, cocaine, cannabis. They are all very common and they have been pretty much restricted by law enforcement agency, and you can see a distinctive difference between the accessibility of these kind of drugs among various age groups and various sexualities. Examples, opiates are pretty much mainly used by males, but however, the non-medical use of pharmaceutical opiates. For example, drugs that are prescribed drugs, but they have been used as an illegal drug for non-medical purposes. So this is quite common across both sexes, both men and women. So the problem with this type of illegal drugs is they are very easily accessible because they can be easily purchased in shops with or without prescription. It has to be sold with prescription, but at times it can be available without prescription. So this is a high risk of easy accessibility to every people. So the WHO and the UN drug agencies are regulating, focusing on these drugs for a period of 10 years. So within a period of 10 years, you can see a 5-time increment of such a new psychoactive substances. And among these, about 87 substances are pretty new. These drugs, the new drugs are designed by slightly changing the functional groups of existing drugs. By changing this way, they can able to retain the sedative activity of the drug, but at the same time, they can escape the standard screening procedure to screen the drugs used. The high risk of these designer drugs is these drugs are not testified. These drugs are not testified for their toxicological behavior. So using of these drugs can be highly fatal and can cause serious side effects than that of the original drugs. Benzodiazepines is a class of psychoactive drug which has been prescribed for anxiety. It has been taken into the market to replacing the problematic gamma-butyric acid, to treat sedation and sleep, to aid sleep. So classically, benzodiazepines as a legal drug. So what is benzodiazepine? Benzodiazepines are a class of prescribed drug given for psychiatric treatment, and they are prescribed to aid sleep, reduce panic, anxiety, and treat muscle spasms. But unfortunately, this has been highly associated with illegal activities because benzodiazepines has a very strong sedative nature. So they have a high ability to bind GABA receptors of the human body. So they can keep the person in sedation for a pretty long time and pretty stable during the sedation period. However, the prolonged use of benzodiazepines, they are highly addictive. So once a person is prescribed with some 50 mg of benzodiazepine, the person will develop resistivity towards the drug. So next time they have to increase the dosage to a higher level. So this prolonged consumption of benzodiazepine make the person addicted to the drug, so they can't able to sustain without the use of this drug. So the withdrawal symptom of benzodiazepine will also be very costly, and benzodiazepine will naturally increase suicidal thoughts, and it lead to high muscle activity, and it decrease the neural activity pretty much, so inactive. And the death ratio of benzodiazepine uses, because benzodiazepine is classically given to treat anxiety and stress. So at the age group of 20 to 50, people of both sex, both men and women, easily get prescribed or get access to these kind of benzodiazepine drugs by legal way or illegal route. So this addiction gives them an escape route of their daily routine of stress and anxiety, but this highly increases the death rate of this age group ranging from 20 to 50. And this high death rate can be accounted thanks to its suicidal thought attempt when the drug is not available for the use, and the activities of the person when they are under the use of these drugs. So controlling this is a main necessity to minimize the risk of health and social safety. So benzodiazepines and its common impact and how it's consumed. So benzodiazepines withdrawals include nausea, insomnia, because naturally benzodiazepines are given to aid sleep. So once they start to withdraw the use of benzodiazepine, when they try to reverse the process, they back to the original states that they have been suffered with, and this time they can't able to retrieve the process so smoothly because it induces depression, anxiety. It multiplies the anxiety pretty much many-fold than that of its original before the consumption of benzodiazepine drugs. So the withdrawal of benzodiazepine is a very hard pathway. So usually the withdrawal times take from a week to a year, naturally from 2 weeks to a year. So the drug can be metabolized and taken out from the body within 2 weeks, but the withdrawal symptoms and the complete withdrawal of the prescription of the drug will take a pretty long time. Maybe some of the students maybe read some Facebook post or Insta post or somewhere or Twitter posts about a pill called a blue pill. Maybe somewhere, somehow, maybe you can come across those term blue pill. So that is a class of benzodiazepine drug. I don't want to say what's the name of the drug or the structure of the drug. It has been there, but I don't want to say what's the name. But it has been a benzodiazepine drug. So that is very commonly associated with drug facilitated sexual assault. So these drugs, you can see the structure. These are a few examples of benzodiazepine structure drugs, and these structures has the benzene ring fused with the diazo ring. So that's how it gets its name of benzodiazepine. And these structures are not soluble in water. So as long as you are taking a water from an unknown person, it's safe. So we have these drugs are not soluble. But these drugs are soluble in alcoholic beverages as well as acidified drinks like juice, apple juice or lemon juice, which are slightly acidic, and these acidic protons are able to protonate these amines and aid the solubility of this drug in that medium. So naturally, benzodiazepines has its own high strong sedative effect, but unfortunately, when in certain places, this has been coupled with alcohol. So with alcohol, benzodiazepine has very high solubility, and alcohol itself is a additive, and added with benzodiazepine, it multiplies its sedative behavior and effect on CNS, central nervous system. So this leads to a severe neural damage and a prolonged addiction problem to the consumer. So in order to control the use of benzodiazepines as a lead drug, it's a clinically prescribed drug. Even now, we have more than 20 benzodiazepines as a clinically prescribed drugs. But those 20 benzodiazepines have been slightly modified through functionalization. For example, they can introduce some chlorine or some fluorine, make the nitro or reduce the nitro into amine. A simple, slight modification of these drugs can form a new class of benzodiazepine. And the pharmaceutical people have studied the toxicological behavior of the classified benzodiazepine drugs, but these new drugs are not taxonomically studied, and they still retain the sedative behavior of benzodiazepine, but impose a huge health risk because the toxicological behavior are unstudied. As a chemist, we all know a simple change in stereochemistry can be a divine or devil. But when we change the functionality of a substance, which is naturally a central neural active substance, if you change its functionality, it can be more catastrophic, less effective. But usually people don't choose for less effective, they go for more sedative behavior. So in this aspect, developing analytical platforms that can detect, that can sense these substances are more welcome. So in this prospect, I develop a platform and demonstrate one of these substances, which is the clozapine. And I have the thoughts of that later. So I say I'm going to sense or detect the substance. So what is sensing? What is sensor? So sensor, every human has 5 primary senses. The sense of vision, ear, hearing, taste, touch. So these are the primary senses of humans. So in that way, how the sense of vision works. So that's the primary sense of a human. So how vision works. So when we see an object, we get the photons reflected from the object, and eye acts as a receptor. It collects the photons and it sends the details of photons, the color combination of the photons. It's a red, blue, or green. What is the wavelength of the photon? It's given the information to our brain, and the brain processes it and gives us the output of the object that we are seeing. So in this scenario, a sensor has the input and it has a receptor to receive the information, and it has a reader and it will produce a result. So this is the general way of a sensor, and because it's a sensing process. That's why it's called a sense of vision. In general practice, a derivative practice, we have a different range of sensors, ranging from a humidity sensor, proximity sensor, IR sensor, UV sensor, a wide range of sensors, which are all electronic sensors. These are classified as electronic sensors. So what is the chemical sensor? The chemical sensors are classified into various groups, ranging from electrochemical, photochemical, optical, mass spectroscopic, electrical, which is a piezoelectric devices. So these are all a class of chemical sensors. So how do we more appropriately define a chemical sensor? So as a chemist, we check the IFAC definitions. So how the IFAC norms define a sensor? A device that can convert a chemical data into analytically visible signal. That data can be a concentration or a composition, a parameter that can be directly converted into a measurable signal. So that sort of a device is called sensor. So now my field of research is developing a device that can measure the concentrations of these leaked drugs from the given sample. So the key terms that have been more associated with the sensors are analyte. Analyte is the substance under investigation. So what's the target species? That's called analyte. Receptor, the species react with the target species. Receptors are the species that are binding with the target species are called receptors. Detectors are the component that, just like our eye, the cones and sticks inside of our eyes are detectors, because that detect the photons that fall into our eyes. The receptor that can be said as a lens, the eye lens that take the light and focus it into the detector. So that can be a detector and a reader, and that can be a detector. The reader is a brain, because that's the where it does the processing. So in chemical sensors, it can be a UV spectrometer, a photospectrometer, or a chemical analyzer, electrochemical analyzer. That's taken as a reader. So some more other terms, a reporter, it's a optical sensing devices. The output has to be photoelectrically active. So it has a specific wavelength. So the product that has a specific wavelength or a specific electrochemical behavior, that are called reporters. Interferon. So in a bunch of crowd, you're looking for a person with a red shirt. That red shirt guy is a analyte. So everybody else in the crowd is our interference, because that everybody else can hide the red shirt person in the crowd. So the coexisting species in the system given to study are all characterized as interfering species. Selectivity, how specifically we can pick the particular person or particular species in the system, that's called selectivity. Linearity, and how good we can study what is the concentration range, the current response or the signal response. It can be in optical sensors, it's a signal response in terms of intensity of light. In electrochemistry, it's a current response. The linearity between the signal versus the concentration or the composition of the study sample is taken as the linearity. Sensitivity is the ratio between the signal and the concentration of the analyte. Assay time, the time taken to measure the maximum output of the signal is defined as assay time. So the chemical sensors, predominantly we use optical and electrochemical sensors. So the general principle, when we place a test sample with a sensor, it has a receptor that reacts with the sample. When there's a chemical reaction, it can be a photochemical reaction or an electrochemical reaction or a conventional chemical reaction. So after the chemical reaction, it produces a signal. So that signal can be either visual, which means change in wavelength, or it produces a new light of different wavelength, or a change in electrochemistry, which means it produces an ion, it transfers into reduced product, oxidized product, and during the process, it transfers some electrons. So that can be studied. So in these two are the most common and very widely adaptable economical options available for chemical sensors. So in these two, we have their own advantages and disadvantages. For example, the optical sensor, you can see visually. So when you have the COVID test kits, when you put a sample, The COVID test kit will give us two, if it is given 2 lines, it's positive, it gives us give 1 line, it's negative. So that 2 lines is a color. So if you see 2 colors is easy, you can say yes or no. So it's a yes or no question is so easy to answer by the optical spectra, which means the visual signals are very easy to read out. But it has a problem. You can't work with opaque samples or color samples. As long as our samples are transparent, we are very well and go with the optical sensors. The moment our samples become colored or opaque or very darkened, we can't able to go with the optical sensors. We have to dilute. With every dilution, our analyte concentration also get diluted. So we have to go a lower sensitivity, a high sensitivity with a very low detection limits. And that make the instrument very big and experiment much more complex. And more importantly, the problem with the color sensor is how we read the signal. Naturally, men and women has a different tendency of reading the signal. So usually boys, men, we usually say red, pink, blue, green, yellow. Maybe that's how we can see the colors. We can't see the 50 shades of pink or blue. So that's able to be done only by women. So that's in case the person who sends the sample for the illegal red, if a man check it's some sort of it's a red, but I don't know whether it's red or which red, we don't know. So in that cases, the risk of false results is very high with the optical sensor. But in electrochemical sensors, if the reading is high, if the current is high, yes, you have the concentration is high, that's it. The higher the number, higher the risk of getting to a charger. So in that prospect, the electrochemical sensors give us the better composition, the better readouts for very common person. So we are focusing on electrochemical sensors. So what are the 3 prospects? The 3 easily available, the easily most common prospects of electrochemical sensors, because electrochemical sensors also include immunosensors, apta sensors, but these are pretty complex and it takes some time to construct and stability problems and economical problems. So 3 cheap alternatives of electrochemical sensors that can be processed. Electrocatalytic sensors, electrochemical transduction sensors, and ion transfer reaction sensors. So electrocatalytic reaction based sensors, in here the system 1, the target analyte have the electroactivity. So it is a redox active, whether it will get reduced or oxidized or get undergo redox reactions under when you supply potential. So for example, in this work, hydrogen peroxide is get reduced into water when we supply when it is electrochemically reduced under the given electrode system. So these sort of reactions can be used to measure the concentration of the target analyte, in this case is hydrogen peroxide, towards a specific concentration range by using the electrocatalytic reactions. So these electrocatalytic reactions using a nanocatalyst or some other materials to study the concentration of the target analyte is an electrocatalytic electrochemical sensor. The class 2, it's electrochemical transduction reaction. For example, here the molecule A, this molecule is taken as A. So this molecule A has its electrochemistry, the redox signal at a given potential of plus 22 volt, the 200 millivolt. When the molecule A reacts with this enzyme, blue, that's marked as a blue, so this is the enzyme. So when the enzyme LAP reacts with the molecule A, it produces the compound B, which is aminoferrocin. It has the redox potential, redox signal at a different potential. It is of negative 150 millivolt. So there's a clear change in potential of these 2 redox species. So it's a biochemical reaction. This biochemical reaction produces a product that has a different redox behavior. So we are studying the electrochemistry as a transducing tool to study the reaction between these 2 species. By studying these 2, we can measure the activity of this enzyme. So this enzyme doesn't have the electrochemical activity of its own. But this enzyme activity can be studied to study the electrochemistry of these species. So this is a transducing species. So this is sort of sensing is called electrochemical transduction sensing. So the type 3 is a ion transfer reaction. So in this is a simple example for you have a membrane. It's a simple example has taken from the biofuel cells setups. So it's a membrane, it has the proton penetrating from left to right. So in this case, when the protons going through this membrane, there is some sort of energy has to be applied to pull the proton to the right side of the membrane. So in order to compensate the flow of proton, you can see a flow of electron on the external circuit. So the ratio of proton flow in the membrane can be correlated to the electron flow outside the circuit. So through this phenomena, you can measure how much proton is flowing through the membrane by measuring the current flowing through the external circuit. So here you can measure. Here we are measuring the ion transfer, not the electron transfer, not the redox species. We are not measuring H into H plus. We are not measuring that. We are see how H plus moving from one side to other side. So we're compensating the flow of H plus, there is a flow of electron in the external circuit. So by measuring that, we can see, okay, this amount of H plus has been transferred. So by this way, we can measure the concentration of the target species. So in simple words, the three classes. The first one, the target has to be redox active, which has to be get reduced or oxidized. In system B, it doesn't need to be redox active, but it needs a redox mediator as a transducing element. In system B, in the system 3, the ion transfer reaction. Here, the system has the analyte which has a charge. It has a charge, but unfortunately, that charge doesn't have its own redox signals. So in that scenario, we see the transfer of these ions across the membrane or across the interface to see how much the ions are transferred and measure the electron transfer due to the ion transfer as a signal. So I have done the principle 1 and 2 before, so now I take the principle 3 right now. So how to make the electrified soft sensing interface that I have defined in the title. So what is in the earlier slide, there is a membrane, but both the sides are aqueous phases, but there is a membrane to make an interface between those two phases. But here, instead of using a solid membrane, we have taken So here we have taken two liquid interfaces by fabricating a soft interface between two liquids. So the electrified liquid interfaces is defined as interface between two immiscible electrolyte solutions. The electrolyte solutions consist of a highly soluble salt, a highly hydrophilic salt dissolved in water taken as a one phase, and a hydrophobic salt partially solubilized in an organic solvent is taken as another phase. So naturally, some of the organic solvents are completely immiscible with water. For example, like benzene, dichloromethane, has very, very low miscibility with water. So when you dissolve the salts that are soluble in water, for example, when you separate the organic synthesis, when you do the synthesis, when you try to remove the compounds that are solubilized in water, you add some salt into the mixture and pour some ethyl acetate or dichloromethane, and you shake well. When you shake well, the salt dissolves in water and it thrown all the organic materials into the organic phase. So it's a similar principle. So that makes the two clear layers between organic and aqueous phases. So here, naturally, you can have two phases without use of any membranes. So you have an aqueous phase as well as an organic phase without use of any membrane. So now we are going to study the transfer of ion between one phase to other phase. Preferentially, we go on to study with transfer of ion from aqueous to organic and organic to aqueous phases. So in this scenario, actually in the first two scenarios of the electrochemistry, electrochemical sensors, in these two scenarios, the signal is due to the redox current. The reduction of oxidation reactions produce the signal, but in the system 3, it is due to the ion transfer of ions across the interface from water to organic, from organic to water. So the transfer of ions is going to produce the current signal, and this is governed by galvanic potential difference of the ionic species. So how it has been demonstrated? So in my system, I take the drug Rosaphene. So I study its behavior. As I said earlier, this is the original drug structure. So the drug doesn't have, has a very big aromatic peloton. So naturally, its solubility in water is almost nil. So I can't able to dissolve this substance in water. So in order to place it into water, it has to acidify it. So to acidify, I make the pH into pH 4. For pH 4, we can protonate the substance, protonate this nitrogen, because the pH 4 has sufficient protons to protonate this nitrogen. So at the pH 4, the possibilities are we have the neutral, we have the positive, we have two positive. We have monocation and dication species. So I recorded the cyclic voltaggramograms by putting this drug at pH 4 into the aqueous phase of the system. So I've given the sample of my actual experimental setup. So it has this is the aqueous phase, and I use 4 electrode system, 2 counter electrodes and 2 reference electrodes. So the handles has a reference electrode. So this is the reference electrode for the organic phase. So this is the reference electrode for the aqueous phase, and this one to go to the bottom of the system. That's the electrode for counter electrode for organic phase, and I will have one more electrode at the aqueous phase as a counter electrode to implement the potential differences. So when I place this substance in the aqueous phase, I have to apply some potential to push it to the organic phase, because you can see when it's a neutral species, it's highly soluble in organic, but I put it in pH 4, so that I can able to make it in aqueous phase. So when I put it in pH 4, I will have the charged species, and charged species can be stabilized in water. So when they are in water, they are not ready to move into organic phase because they are having their own charges. So it has the 2 compositions, the mono and dicationic species. So we can see 2 different peaks at applied potentials of 500 and 700 millivolts. So these 2 peaks can be corresponded to monocationic and dicationic. The A is corresponding to the monocationic and C is corresponding to the dicationic, because as you can see, the monocationic species require less energy to transfer the interface, and dicationic species actually naturally need more energy to go across the interface. And the reactions can be reversible from the organic to aqueous, vice versa. So now I have studied this drug can be studied by measuring the transfer between these 2 interfaces. So I can study its concentration because I can see this drug is interfacially active. So it's not we are speaking about redox activity, we are speaking about interfacial activity. So this drug is interfacially active. So now I can go further to study its dependency over concentration. So to study to have a clear idea of how this drug will working across the pH, I studied the effect of pH because I studied pH 4. I have 2 peaks. It has 2 peaks of monocation and dication corresponding to mono and dication of the species. So now I know this drug can be exist in 3 forms. It's a neutral, mono, and dicationic species. So how it will vary at different pH. So for that, to measure the interfacial activity, I check the CV of this drug with a different pH ranging from 2 to 9. So I have studied, when I observe the current, I can notice the current values dropped drastically when I go higher in the pH. So I check the molecular partition diagram, the theoretical fluctuations and the experimental parameters. It shows when the pH is increased, the drug go into neutral form. So as long as the pH stay below 5, below 6, as long as it stay below 5, the drug preferentially stays as ionic species. When the pH go beyond 6, it prefers to be neutral species. And this is further confirmed by the mole fraction diagram by plotted using the pKa values of the drug. At pH 2 to pH 3, you can see all the species, almost 100% is 2 plus. But when the pH is increased further to pH 4, 1 plus becomes 50%. At pH 6, 1 plus is 100%. And at pH 8, you can see almost 100% is neutral. So in this way, I know this drug is interfacially active. When it's charged, well, only it's charged, I can see the interfacial activity through the transfer of ion current. So I have to study my experiments within the range of pH 2 to pH 6, not anything beyond, because after pH 6, I see a huge loss in the concentration of this charged species. So now I have the problem, because these drugs are usually, the objective of my study is to study the clozapine drugs in samples that are highly associated with DFSA crimes. So the DFSA crimes are mostly involved in use of ethanol. So the system that I have formulated as a clear aqueous phase and the organic phase, they are highly immiscible. But the test subject that I'm going to explore with has ethanol. Ethanol can be solubilized in both aqueous phases and organic phases. So it can, the ethanol in the substances that I'm going to study may destabilize the interface. So when the interface has a clear structure, we can see the transfer of ion across the interface. The introduction of ethanol can destabilize the interface and that can collapse the system. So now I have to study how much my interface is stable with respect to ethanol and how it can study the activity of the drug. So for that, I have studied the effect of ethanol concentration ranging from 0 to 10%. We have 0 is a natural juices or simple drinks without non-alcoholic beverages like juice, the carbonated drinks. 1%, 5%, and 10%. Because usually the alcoholic beverages has the ethanol percentage of beer, the drinks like have some 5 to 8%. And vodka is a maximum of 40%, and you can do a 4-time dilution. That's not going to make the concentration much lower for the analyte. So I go for 1 to 10% of concentration of ethanol and study the relativity of the drug, activity of the drug across the interfaces. So when you can see that when you use the pH 2, just the acidified medium, we can see 2 different peaks corresponding to the mono and dication. But with the introduction of ethanol, the second peak is normalized. At 1%, at 5%, it's almost invisible. At 10%, it has no evidence, it has 2 peaks. This system has shown a good linear range, and I get the linear range about 10 to 150 micromolar, and LOD is about some below 5 micromoles, and LOQ is about 10 to 25 micromole, which is very good because usually this pills has more than 100 micromoles of concentration. So when you take a juice and you just put it into the solution, you test the samples, that means it has the concentration of above 100 micromoles. So far it's so good, so I can go for the real samples. The sensitivity is appreciable, and it has a KD value of 10 power 5, which means the neutral species is 5 times, 10 power 5 times highly soluble in organic phases than the aqueous phases. And the standard governing potential of the drug is about 125 millivolts. So now I know the parameters, I know the analytical parameters, and what is the LOD and what is the linear range, how it's the sensitivity. So now I can go for measuring the performance at the real sample. So for this, I have taken the systems using alcoholic as well as non-alcoholic beverages. So as I said earlier, I just keep the system to acidify to pH 2 to make sure I have the drug as ionic species. I use a HCl to acidification because that's the easy reagent. Because the principal objective of the study is to have the rapid analytical system. So we don't need to use a very standard measurements to make the exact conditions. Very defined conditions which are laborious. We have to take the sample to the lab and measure that. We are not going to do that. We are focusing on making a system which is ready to do it on in situ. So in that case, we use a simple reagent like a HCl to acidify the system to pH 2, and after pH 2, we measure the response ion transfer current from the aqueous phase to organic phase by spiking 100 micromolar of the drug. So vodka with a 10% of alcohol, which means diluted 4 times, with 100 micromolar of the drug at pH 2, produce a clear increment in the current signal, and the subtraction of the background current give a much evident signal of the response current. So the vodka with apple juice, vodka mixed with apple juice, under similar circumstances, produced a much clear response current for the presence of drug. However, with apple juice at a pH 2, the response current is notably very low. For a concentration of 100 micromole, this is 2 to 3 times lower than that of the signal observed in presence of vodka. So this gives us a clear alarm that what we have done earlier with a different percentage of alcohol is not going to be useful for our whole studies. So this problem open our eyes to study the behavior of the drug with the individual samples. So for pH 2, actually it has to be high. It has to be high for the interfacial activity, because from the earlier composition diagram, olfaction diagram, we see that at pH 2 the drug is almost 100% 2 plus. So this has to be have the highest interfacial activity, but with apple juice system we couldn't able to get the best current performance of pH 2. So I studied the impact of pH at apple juice. So naturally the apple juice is at about 3.8 somewhere in pH, 3.8 to 4.5. The range is 3.8 to 4.5. So it fluctuates in the range with the different sources. So I make the juices into a standard pH of pH 2, 4, 6, 8, and 10. I studied the activity of interfacial activity of the drug with a different pH of apple juices. So in this case, I can able to see the natural pH of apple juice is somewhere near 4, so the 4 is not bad. At 2, it drastically drops down. At pH 6, it maxes out. So in this scenario, we can see that the coexisting species in apple juice, they have a high electrostatic attraction with the clozapine species, with the dication quotient. So the electrostatic attraction is so strong, so it restricts the interfacial transfer of that dicatonic species across the interface. So at pH 4, from the mole fraction diagram, you can see from the at pH 4, you have 50% of dication and 50% of monocation. At pH 6, you have almost 100% of monocationic species. So the monocationic species are relatively has a better interfacial transfer ability than that of dicatonic species, so that we have figured out. So we use pH 6 for the apple juice system to study further. So these experiments give us a conclusion that the earlier calibration plots that we have obtained using a standard system with a different percentage of ethanol is not going to work for each sample, because each sample has their own composition, and the composition has played a critical role in affecting the interfacial ion transfer reaction. So to get rid of the situation, we study the interfacial activity of the drug with a different real sample system that we have taken for our studies. So I study the different concentration of the drug against vodka, apple juice, and after the corresponding calibration plots, and the same situation has been studied with the vodka plus apple juice, wine, and beer. So with beer, it's very interestingly, the response current, the ion transfer current is very low, but it has the very highest background current. Beer has the highest electrolytes in the system, but the high background system current will gradually reduce the response current of the drug. So under these circumstances, we can able to measure the drug with a range of 60 to 180, which is well above the range of drug that can be possibly found in the DFSA crime samples. Usually the DFSA crime samples have these benzodiazepine drugs in higher 100 micromoles. So with even 10 times of dilution, you can still able to find some sort of concentration in low micromoles, which is above 50 to 100 micromole concentration. So the system has a linear range to 60 to 180 is very apt for the real-time application. The LODs are just about 20 to 30. The LOQ, that's the objective, the principal values, that can be in the 30 to 50. So this is still well within the range of measuring the drug under the system that has been reported in the DFSA samples. So later we just spike the samples that we have studied with the standard concentration of drug, which is 100 micromolar, and we able to found the recovery rates from 104 to 109, so which is less than 10% of related standard deviation. So the findings so far, the clozapine has the interfacial activity at a liquid-liquid interface, and the effect of pH has been studied because the drug has a different molar composition, depends on the pH, and that greatly impacts the interfacial activity of the drug. And we have studied the interfacial stability of the system in presence of ethanol at a different composition. And we have measured the interfacial activity and the analytical performance of the drug with different concentration of ethanol, and it has shown a linear relationship, and it shows the significant drop in the chemical composition of the drug with increasing amounts of ethanol, because the neutral species are more likely to stay in ethanol. They don't want to be transferred into the aqueous spaces, though we can able to see only one peak when we increase the number of amounts of ethanol in the system. So the LOQ of the study, the limit of quantification of the real system, is about 30 to 50 micromole, which is well within the range of the drug that has been found in the real crime samples. So the spike samples has shown the RSD below 10%, which is the theoretically acceptable threshold. So it's okay for a primitive device. So what's the future? So the future is about making a 3D printed micro device that can be portable and use very minimal samples, because in this system I have used about the sample size of our average of 5 ml in total, taking the organic and aqueous space together. But to make it more practical and more commercially viable, we are planning to make it 3D printed models to bring down the samples into microliter amounts, and that eventually increases the sensitivity, and that will give us the better RSD values for the future. So this is the talk. So I'm pretty happy for the opportunity given by my dear professors, because I'm a proud student of this Xavier. And I'm thankful for all the students, participants, and the teachers who have been at the event. So if you want to communicate with me further, you can drop me an email. Just write my name and followed by the email extension. Thank you, and thanks. Any questions?
Any questions from the audience? Any doubts? If there is no questions from the audience side, we can conclude the session. So actually, Balamurugan, you were, I think, our friend, and so that I said like that. So Dr. Balamurugan, it's really a very interesting presentation. So I observed that you started with the drugs called
Yes.
benzodiazepine as your base, and the same as a drug, and another side you have alcohol as an acid, and you showed a beautiful mixing process because they are you can mix these two with the principle of an acid base concept, and slightly there you moved towards a sensor concept, and you applied the same for the analytical techniques, and
Yes.
and at the final you concluded with the identification of these chemicals in other beverages and some other drinks. So it's very interesting for us. The way you took the session is very clear, and it is very beautiful for us. So on behalf of
Thank you.
behalf of the Department of Chemistry and my own behalf, and the behalf of all the participants present here, we extend our warm thanks to you for your presentation. Thank you very much for your contribution and the presentation. Thank you.
Thank you for that. Thank you, everyone. Thanks for the opportunity. Thanks for the time. Thank you.
So we have another 7 persons to present their oral presentation. We can have it in this call now. So those who are here to present your oral presentation, you please come forward and wait. We can start at the earliest now. So those who are presenting, please come forward and we can go for the presentation.